Bismillah ar-Rahman ar-Rahim. Welcome back to our course, Deep Learning for Computer Vision. Finally, you arrived at the deep learning part of this course. Our today's lecture will be the 19th lecture, and it will start talking about deep learning. So the title of this lecture will be an introduction to deep learning algorithms in general. So let's jump to the lectures, slides, and try to discuss a few things there. So today we'll talk about the deep learning. It's just a soft introduction about the deep learning in general and what are the types of deep learning, etc. As you see from the sessions guideline, we'll talk about deep learning in general, how we will define the main items in deep learning, the main idea. We'll talk also about the types of deep learning approaches and algorithms. We'll also talk about some additional approaches that are related to deep learning, and they were not very well known when we talked about the machine learning approaches. In general, deep learning, as you know, it's machine learning, part of machine learning techniques or machine learning approaches that can be used with stronger output quality, with better performance, but it requires a highly condensed computational cost, and it provides and helps us to deal with different types of input data, including text, images, let's say data sequences, data points, etc. All these things can be dealt easily using deep learning approaches, as will be clear from the rest of this lecture and the coming lectures regarding deep learning. Let's see, here we have the input to animals, dogs and cats. We can use deep learning, deep neural network to classify it into the proper type in this situation. This is similar to machine learning. However, we may add more features and more classes and more hidden layers to get the output with a high accuracy in this situation when we're using deep learning or what is possible using the machine learning approaches. Also, as you see here, we can use it for object detection and localization. Here we have anchor boxes with the accuracy or the confidence measure of every of these components, like this car or this person or this traffic light, etc. All these things can be done using what we call it a very important or interesting deep learning approach, which is the YOLO versions. It will be discussed later on, maybe at the last of this course. So what is deep learning in general? We discussed this issue in previous lectures. However, let's have a let's go back in a quick tour to describe the deep learning. Deep learning in general is, as we all know, it's a subfield of machine learning. So it's a machine learning approach, but it is something advanced on machine learning because it is concerned also with algorithms inspired by the structure and the function of the brain, what we call the artificial neural network. So in general, it repeats again the main concept of the machine learning because it is related to the human brain and it mimics the human brain neural networks. And this is why we call it as a machine learning, advanced machine learning approach, but with stronger capabilities and with higher performance at the output of the required tasks. Now, in deep learning, as in machine learning, we try to perform different tasks. This includes detection, classification, regression, segmentation. These things can be done in machine learning for input data or maybe signals, but in the case of deep learning, we can apply this directly to images, to text, and sounds. So it has been broadened. It's broadened when compared to machine learning because machine learning could not directly deal with images at the input or maybe videos in other cases. So this is one of the advantages or benefits of using the deep learning. The term deep means deep is usually used because we are going to use more and more complicated or more layers and stages of the neural network, maybe, and the machine learning approach in general. So in general, when we deal with neural networks, we may have 2 to 3 layers, maybe more or less. But in deep learning, we can apply tens or maybe hundreds of these hidden layers to improve the performance of our machine learning system, which is in this case the deep learning approach. As you hear from this slide, on the right hand side, if we can zoom it a little bit here. So we repeat this idea again that when we deal with deep learning, it's a part of machine learning. Machine learning is a part of artificial intelligence. It has some overlap and intersection with the data science in general, computer applications, and the deep learning is very specific and can be used intensively in all these directions. Here it's sort of in joke that we are concerned not only with increasing the artificial intelligence performance, but also we want to increase the real intelligence, because when we rely on artificial intelligence, we may sometimes lose some of our strong points or our strength on memorizing things, because we can use of the artificial intelligence in performing many tasks and issues. However, this is the task these days, and this is the trend, and it will be continuing maybe for the next 2 or 3 decades, and who knows, maybe more or less. Anyway, it will be very beneficial to learn and to know and to apply deep learning approaches in your life, in your engineering applications. Wherever you can do this, you can do it again using deep learning. Sorry. Okay. Now, in fact, the machine learning or the neural networks, it was a long time before it started to rise, because to land off or for takeoff. Because in case of using neural networks, when we have heavy, a lot of hidden layers and deep neural network, in this case, it requires very complicated or very strong complexity and computational cost. And at that time, when this started, maybe 20, 30 years ago, there was a shortage in computers facilities and in the processing units, especially because it requires strong, maybe not CPUs only, may use also GPUs, graphics processing units, and this is the main reason of the delay in the rise of deep learning. So now, after the increase, the evolution in the powerful techniques in producing supercomputers and very speed computers for in calculations and with high memory applications, the deep learning has found an application, and it has its own rise these days. Now, if we want to compare machine learning with deep learning, we may look at this table here. In fact, when we talk about many facts here, we can maybe take the data requirements. When we talk about deep learning requires large data, so it requires a large memory, it requires a strong processing units, while for machine learning, this can be done easily. So this is, let's say it's a sort of disadvantage of deep learning when we need more or large data for processing and for performing our system. When we talk about the accuracy, so the output accuracy, the performance of the system, here one of the advantages is that the deep learning provides us with very high values for accuracy, and it is sometimes maybe up to 100% in some systems, while in the machine learning, the accuracy will be a little bit lower, and we'll get lesser accuracy when dealing with tasks using machine learning. Now, for the training time, in case of using deep learning, it takes a lot of time. It needs a very heavy training, and this leads to a longer time for training. While for machine learning, it may be little bit, or when compared to deep learning, much less time it requires for training. This can be seen when we compare the speed in both cases. So this is again a disadvantage here. So what we take here, we could reach, this is a disadvantage, this is an advantage, this is a disadvantage. Now, hardware dependency, usually in deep learning we need GPUs, graphical processing units, and sometimes we may use TPUs, which is the Tera processing units. These usually are available when we deal with cloud computing. Now, in case of machine learning, we have just to use the CPUs. So again, this is a disadvantage. Now, hyperparameter tuning can be tuned. The parameters in the case of deep learning can be tuned in various different ways. So this is again an advantage because it makes the parameters more adaptive to the to the task or the proper processing that is required in this situation. And this is for the machine learning is a little bit. It has limited tuning capabilities. When you look at these parameters, you can see that the major or the main part that we are going to deal with and the advantage that can be achieved is when we deal with deep learning is the high output accuracy as an output, and it has also the ability to tune my parameters according to my task or my specific problem. Not only that, because sometimes deep learning goes beyond that by adding new functions, new applications, and new approaches, and it solves a lot of problems that were not be able to be solved using machine learning. This is one of the ideas behind the advantage of using the machine learning, the deep learning over machine learning. If we go to the curve, when we compare the amount of data with the performance, you can see that when you let's say add the amount of data in your application, you'll see that when going with time with the performance, you'll see that the performance of the machine learning will be at the first will rise on, and it will go to a asymptotic line where this performance will stop somewhere at this point. It may be 70 or 80% for the accuracy, for example. However, when we deal with deep learning, here you see that the curve is rising up, and it continues rising with increasing the number of data. This means that in case of deep learning, the approach is more flexible and gives us an ability to increase the performance while it requires also an increase in the input data. This may be a disadvantage, but it's still when we increase the performance and improve the performance of our system, this means that we are in the right way to improve the performance of our systems in general, at the expense, of course, of having some extra effort, like like increasing the size of the network, and by increasing the requirements for memory and for calculations for the CPUs, GPUs, the processing units that are required in case of very deep neural networks, actually. And this is not the case for all situations, for sure. Now, again, as in machine learning, types of learning in DL are following the same structure as in the case of the machine learning. We have supervised learning, unsupervised learning. We may get some in between, which is the semi-supervised, and the reinforcement learning. These are the main types of all these things. The main, in fact, all the tasks done by machine learning can be done also by deep learning. Now, you may have a look at these functions here, maybe, or what are the tasks that can be performed using machine learning. The same thing is repeated with deep learning with more or better performance and higher outputs, higher output results with wider, let's say, data sets that are applied to such algorithms. The same thing here, the deep learning is, or it has the same functions of, or the types of machine learning algorithms and learning types. And here you may sometimes go to see the deep learning framework. You can find all these systems and that can be available mostly free, like the Cafe, the PyTorch, let's say the Cafe, Keras, TensorFlow. All these softwares and frameworks are freely available for deep learning, and you can access all these resources easily. And it's one of the benefits of having it's a performance that is, or it's an advantage of having a deep learning system, because you can get a lot of data, a lot of data sets, a lot of techniques, structures, let's say algorithms that can be just to drag and drop and modify according to your task. Of course, we can here also use what we call it the transfer learning, because when you train some system and some data to get some outputs, now you can, given a very large data set like what we call it the, what are the available in the frameworks or the resources, you can modify this system or this network and apply to your own data by applying very small, negligible changes to the block diagram of your system, and you can repeat and get benefit of what was done before, let's say by Google, by other types of algorithms and techniques. This will be clearly described and discussed in details in next lectures. In supervised deep learning, as in machine learning, the network in general learns to make predictions or classify data based on labeled data set. So this is the main idea of supervision. So in supervised learning, you have the input, you have the labels of these inputs. The inputs are the data set and the labels for this data set. And you just modify your weights and your biases in your neural network in order to make this input get features and go directly to this class maybe, or this output specifically for continuous or for discrete data. And this data is by default is labeled, totally labeled. So you know from the beginning what is the output label for this input specifically and for all inputs in general. Now, this is again, we repeat the same idea here for deep learning. It is a supervised deep learning approach, similar to the machine learning supervised learning approach. And here we have to work on the cost function or the cost error that comes from the difference between the predicted and the actual targets. And in this case, we are talking about the backpropagation. Similarly, we have it in the deep learning. In deep learning, algorithms like the CNNs, convolutional neural networks, let's say recurrent neural networks, they are used very similarly in deep learning in supervised tasks like image classification, image recognition, sentiment analysis, language translation, etc. So we can extend the region of application or the margin of the machine learning by using convolutional neural networks, for example, and recurrent neural networks to get supervised learning approaches to deal with image detection, classification, labeling, localization, recognition, etc. The list is very long, and you can apply it in case of using deep learning over machine learning. In fact, in machine learning cannot deal directly with images and videos. You need to somehow to modify and get a simplified version of the input by having, for example, the features or maybe some vectors or applying key folds, or you divide the data into subsets, or to convert from to reduce the dimension from 2-dimensional or 3-dimensional to 1-dimensional. And this case is usually not very proper in case of images. In case of the unsupervised machine learning, we know that in this case the data is not labeled from beginning, and you try to discover the patterns and the features of the inputs and to cluster the dataset specifically for the unlabeled data in this situation. Here there is no target variables, so you don't know exactly what is the output that will be or what is the label of this input. And in this case you need to have self-determined you try to explore the hidden patterns or relationships within the data sets. The same thing is true for the deep learning, as well as it was the same for machine learning. Now deep learning sometimes also goes beyond, let's say, the machine learning by adding additional approaches like the autoencoders, generative models that can be used for unsupervised learning. Also, it can be used for clustering, for dimension reduction, anomaly detection. It can also be used for detection of fake images, fake videos, fake scenes, etc. All these things can be found and in deep learning, and it was not actually very clear in the case of the machine learning. Reinforcement deep learning, again, it repeats the reinforcement machine learning algorithms. In this case, the agent learns from his from trial and error, from his mistakes, and from getting an award from positive or from correct answer. And this makes the agent learn to make decisions in an environment to maximize a reward signal. And the same thing is true for deep learning as well as for machine learning. Now the agent interacts with the environment by taking action and observing resulting rewards. Similar, this slide is similar to what was discussed and explained in case of machine learning. We just replaced ML by DL. Of course, there's a difference because here we have deeper networks, we have more calculations, we have better performance. Now we can find deep Q networks. As machine learning Q networks, we can find deep neural networks or networks, deep deterministic policy gradient, DDPG. These things can be used like for today's applications in robotics, in game playing softwares, etc. So we can describe now three main types of DL: deep neural networks, DNNs, convolutional neural networks, CNNs or DCNNs sometimes, and the current neural networks, RNNs, deep RNNs. Let's go with DNNs. We all know what is an ANN. It is a neural network containing an input layer, maybe hidden layers, and an output layer with its own parameters like the weights, the biases, the activation functions, all these things. Now, what is the difference between the neural network ANN and deep neural network? If you look at this picture at the corner, zoom this one. Here we can make the system learn from input images, or it can train itself. We have here input layers. So here we have input. This is the input layer. And here we have a lot of, maybe here just 3 hidden layers. But in case of deep learning, we may expand this to hundreds of such, let's say, hidden layers. And it is a classification task because we have the output specific names like Joey, Chris, Lee, etc. All these are inputs. You can use it for classification applications, can use it for recognition again. So in all these cases, the machine learning and deep learning is similar, but as I mentioned, I am repeating again and again, it has more complex system. It has it can deal with larger data sets. Requires maybe it or implements very large number of hidden layers, and it gives you better performance when dealing with deep learning over when we deal with machine learning. So in both cases, we are trying to learn from complex nonlinear relationships from the input data. In general, why not stack more and more hidden layers and benefit even more from the hidden layers? So this answer sometimes not always yes, because you can add a large number of hidden layers, but you may get to a value or a number of hidden layers where additional increase in the number of layers will not lead to better performance or to increase the performance of the system. And this will be also discussed in future lectures on how to bypass this issue and to improve the quality of our system in performing well for different tasks. Of course, when we talk about deep learning, we are very concerned with the deep convolutional neural networks. The main, let's say, gift of deep learning is the deep convolutional neural networks. In CNNs in general, CNNs are inspired by the organization of the virtual cortex because it deals with input images and it tries to repeat what is or mimics what is our brain is doing with the input data and how it classifies or maybe detects some features or objects in these images. Similarly, we try to repeat this by using the CNNs. Now, in case of CNN, CNN in general is known for its superiority over other ANNs because they have an ability to process visual data, textual audio data directly from the inputs without the need for sort of transforming or dimensionality reduction or other approaches. And this is one of the positives or the advantages of using the CNNs. In general, in a CNN, as you see here, as you see in this figure below, here we have the input image. This image will be applied to the convolutional layer. Here we have the convolutional layer. Of course, here we have a series of filters, maybe a large number of filters that will be applied to the image, and the convolution operation will be operated and done. Then we have another important part of the system or the CNN. It is called the pooling layer. Here we try to reduce the mainly to reduce the spatial temporal information and increase the feature information, which we call it here with the feature maps. And then after getting the proper feature maps that will be help us to let's say get a final or a proper output. It will be flattened and converted into a fully connected layer, applied to a fully connected layer with a neural network. And lastly, we have the classification layer. For example, if we have a classification layer or classification task, we add a classification layer in the term of a softmax layer, for example, or other more or less other techniques also can be used. And this is mainly the CNN and how it is constructed in simple words. So as we have seen here, we have four major parts. It's the CNN or the convolution layer, the pooling layers, fully connected layer, and the classification layer. In case of deep recurrent neural networks, RNNs, or deep RNNs, in machine learning, we talked about RNNs. It's a very specific case of NNs where the output of the neurons or the perceptrons is fed back to the input, and it has a sort of, it can perform a direct cycle forward and backward, and it can memorize the previous state of the system of the data. So this is a simple neural network system. As here we have here, these are the input layers. Now we apply it to the hidden layers. Of course, we're talking about deep RNN. We have a lot of, or maybe tens or maybe more or less hidden layers. And at the output layer, we just keep, in case of the neural network or deep neural network, the output directly from the input data. However, in this situation, we are just going to feed back the outputs from, let's say, from the output to the to the previous neurons, maybe not to one layer, maybe more or less, depends on the type of connection in the RNN. So this will benefit us to keep tracking the output and correcting this output in a feedback system. Of course, RNN, it's very clear that they are very suitable for cases when we have time-related data, and they are used in time series forecasting, for example, because when we use a loop that's capable to remember the past data and use it to predict what will be next. For example, in forecasting, for weather forecasting, for marketing forecasting, all these applications are very are good candidates when using recurrent neural networks. The main issue here is that the computation cost is high, and mainly for the time. The time is consumed very highly in this case, specifically when we have a lot of hidden layers with a lot of feedback connections in the RNN or recurrent connections in the RNN. What else? So these are mainly the types of machine learning that are simply transferred to deep learning easily. And these are the main types of, let's say, DNNs, deep neural networks. We have deep CNNs, deep convolutional neural networks, deep RNNs, deep recurrent neural networks. What we can also find, the list is open. It's every day is updated. Maybe not every day, maybe every, let's say, for a while. However, the topic is exploding these days, and I think that within the next 10, maybe 20 years, we'll still be witnessing, let's say, very strong progress in this direction. For example, when we talk about deep learning, we can also talk about what you call it, the autoencoders. The autoencoders, it's a sort of machine learning approaches where we apply, we have two parts, the encoder and the decoder. Now the encoder tries to shrink the input data from the temporal and spatial domain into the features domain, and finally it will get what we call the bottleneck or the code, where we reduce all the input data in terms of simply in the output. We just get a very short code that represents the main features of the input data X. Now this is the forward direction. Now in the opposite direction, when we uprise or we upsample, we go from the features domain up to the spatial domain and go back to produce a new value for the input X. In this case, we have, for sure, it will not be exactly as the same as X, as here we have the Mona Lisa image. Here we have the Mona Lisa image as you see here. Okay, this is the Mona Lisa, and this is the output. Of course, this type, for example, for communication students can be used for denoising applications, denoising, for correcting some errors, some problems caused by maybe when we have an old picture and want to improve its quality. It's not only the case, it has a lot of applications. However, in this case, we have an input applied to the encoder. We get at the output, reconstructed the output. It's a sort of unsupervised learning, having two parts, encoder and decoder, and the result will be producing, in this case, very close to the input similar image. You may ask why we need very close, and to have a very big and complicated system like this one to get. In fact, the difference between these two images will play a vital role in your specific consideration. For example, in case of denoising, improving the quality, having a grayscale image and trying to colorize this image by adding extra information by using the encoders and modified versions of these encoders, of course. We also have what we call the transformers. So what are the transformers? It's an approach. The transformers are an approach of what we call it generative modeling. This can be done using deep learning. It's again a supervised learning approach or task where we can use the encoders. As you hear, it's a good example on, let's have a pen. Okay, yes. So suppose that this is the input. You have a statement in, I think it would be maybe in, I think it's French or maybe Spanish, I'm not sure. Anyway, you can apply the encoder many times, and you can apply now to different decoders and get a sort of translation of the input data to English, for example, or maybe to another language. So that ultimately I am a student. So you can apply auto translation. You can see this in many applications like in YouTube when you can add translation for any video that you cannot understand its language. It can be found in Google in a lot of applications. This is based on deep learning, and it is based specifically on using the transformers in deep learning. These are other approaches also for deep learning. It can be found also for machine learning, but again, the complexity, the performance, the processing, all these things are in deep learning are made different and stronger. What we can find also in this direction, in fact, very important application is what we call the generative adversarial networks, the GAN or the GANs. So what is the GAN? It's actually a piece of neural network component that can be used to learn useful representation about input sequence or set of data points. Now, as you see from this image on the left side of the screen, now the input X is applied to the generator, which is a source of a type of component that is added for the GANs, where it produces for you a function, the gx, which is the generator function. And after that, you can apply the input again and apply both the input and the generate function here to the discriminator. It's again another part of component that is prepared or that is constructed using machine learning and deep learning. And you can, as a result, describe the input as being either real or fake. So this is the training stage. You train from the beginning, you know X in these cases, and you try to find out get the label for or the class of the data generated here and mark this data either real or fake. Now, if you can next apply your system and give it to other, let's say, some person to apply his own input, and having your input here, you can compare these two different inputs, the X your own and the Y maybe received from a channel, maybe sent you by from someone else, maybe produced by a computer, etc. Then you can now define whether this is real or fake. Mainly, this is the main topic behind the GAN. In fact, it's a little bit out of scope of our application. Maybe it's an advanced approach. It can be used maybe in a future course. Now, if you look at the images here below, the main idea behind the GAN can be also used very easily. Suppose that you have a data set, and your data set is not enough for you. Maybe you have maybe 100, maybe 1,000 samples, and you want to enlarge this data set to be 10,000, for example. In this case, you can produce fake or generated samples and to avoid getting complications in the training of the system. For example, in this case, we have these faces or these, for example, this is a data set for, let's say, face recognition, face detection or recognition, and these images are actually generated by the GAN, and these are not real people. They are AI generated, or they are generated using the GAN approach. So you'll not be claim that do not use my face or my picture in your system, you can improve your dataset by producing new samples in your dataset that are not real faces or not real, let's say, objects or maybe samples in general. One of the very interesting approaches of using these GANs is the deepfake, and it's now it takes out of explosion and over the internet, and I think it will be in future will be a very interesting field of applications. Again, we're not going to talk about this in our course. However, it's good to have some info about it. We repeat the same thing as we used in the GAN. If you look at the block diagram, here this is the input image. Let's say a face A. We have the encoder, we have the decoder, and in the intermediate stage, maybe at the encoded part or the bottleneck, we take another image from another person, for example, and we try to repeat the same process and get the latent face B, and we just switch between the input phase. So what we do here is to switch this image or this code by this code and continue our step. So the encoder part is done for both as usually. However, when we go to the decoded part, we replace or exchange the original by the fake one, and this will lead to get some images that are or some maybe videos that are fake. And today we can find over the internet a lot of applications that can be done using this way. And as you see here, we have one of the images is the original, and the other one is the fake one. Can you find from the images here, or can you note which one is the fake and which one is the, zoom it a little bit, which one is the fake and which one is the original? I encourage you to search the internet and see the difference or how we can distinguish these things. However, I just give you some, let's say, little information. If you look at the lips here, and the lips here, maybe at the eyes, maybe also at this part of the face. Let me make it run now. You may distinguish the difference between the two videos or the two sequences. What do you think? I again encourage you to go and see some info about these ideas and how we can generate systems that can detect this fake. So we are in a big fight in real life between the good and evil or bad, and between fake and real. And we produce systems that produce fake images, fake videos, and we produce systems that detect the fakes or the fake part. Sometimes if it is required for sure. And the process will be fake, anti-fake, fake, anti-anti-fake, anti-fake, and etc. We'll continue to a long a list of systems that can be used in this situation. I think for today this is done. That's all talks, and hope that it was enjoyed. You enjoyed this lecture, and we'll next time go to more details about deep learning, and hope that it will be very simple and straightforward for you to understand and comprehend these topics. Thank you for listening, and see you soon.